Hey everybody, we are back with another guest speaker session, and today we have Tassilo Wald with us. Tassilo is basically a Ph.D. student at German Cancer Research in the Division of Medical Imaging in Heidelberg. His research focuses on pre-training for 3D medical imaging analysis, and he recently had a publication in ICCB, which he's going to talk about. He is currently interning at Microsoft Health Futures, and he has been working on the Human Radiome Project as well. So he's going to talk about self-supervised 3D learning and 3D imaging today. Over to you, Tassilo. Thank you so much for joining us today.
Yeah, thank you so much. Let me just share my screen. All right. Yes. So today is about a recent project that I've done with collaborators. It's called an OpenMind for 3D medical vision self-supervised learning, which was joint work together with Konstantin Ulrich. You can see him on the bottom left. Let me get my laser pointer here. And with Jonathan Zubriadi, a student of ours. And since this is like a recent project and a follow-up basically from a previous paper, we'll also talk a bit about the revisiting MAE pre-training, which started like this whole journey of ours. And to pick you up, we were starting this in like 2024 or like late 2023 in December, and we were like in talks with a collaborator, and they wanted to do self-supervised learning, and we were wondering why no one is using 3D medical self-supervised learning at the current state. I mean, we were doing a lot of medical imaging and like a lot of self-supervised learning, and we were wondering, like supervised learning in segmentation, and we were wondering, why do we still train like our 3D medical models from scratch? Maybe sometimes we use some supervised pre-training, but we were just wondering, like, where's all these self-supervised models at that you can see in the natural imaging domain, where you have your clips and you have your Dino V2s. Why don't we have that in the medical field, and why does no one use it? And with this question in mind, we started a bit of a literature research and went to like Scholar and looked for medical self-supervised learning and found this VOCO paper. This was published in CVPR 2024, and wanting to like get a feel of the entire domain, we started off like with some questions like, what data sets do these papers pre-train on? What common benchmark data sets are used? Which architectures do they use? How do they do their downstream evaluations? Do they do segmentation or classification? And on which data sets? And how good are these models in general? So like, what kind of performance benefits can you expect when you start with medical self-supervised learning in 3D? And given this paper, we, with these questions in mind, we skimmed through it or like read it and looked for like key phrases describing this. And we found like statements about the pre-training data set sizes being like 1.6K CT scans here. Then regarding implementation architectures, we found like Swin Unit R as a architecture. And then as downstream data sets, stuff like BTCV, LITS, MSD spleen, BRADS 21. And given like these keywords, we were like a bit surprised because if you look at 1.6K CT scans as pre-training, it's like not that much data. If you look at, for example, Total Segmentator, which was public at the time, it came with 1,200 CT scans, which are supervised. So the data scale is not really that much higher as you would like hope for. And same with the architecture, we were like, since we are like in the segmentation space, not really like that convinced that Swin Unit R is really like a state-of-the-art architecture. We've just done like a benchmark study recently, NN Unit Revisited, where we like checked out all these new architectures and these fancy Mamba architectures or transformer architectures, and Swin Unit R just didn't perform that well. So we were not really sure if like performance improvements on Swin Unit R would translate to performance improvements once you're at the like performance optimum, like or like the performance limits as you are in NN Unit or MedNext regimes. So we are not convinced. And also the evaluation and that we've seen, in the same study, we also like evaluated the quality of a data set for benchmarking. And a lot of the data sets that were used, like BTCV, BRADS 21, you can see them very low here. And these data sets are just not like that good in like yielding consistent results, and allowing one to distinguish if a model actually performs better than another method. So we were a bit unsure, like if this means the method is good or not, and what performance you can expect. So we like kept searching. And oh yeah, one last point I forgot is that since we are like the NN Unit lab, which is like a automated segmentation method that is very prominent in 3D, we were hoping to see it because it's usually self-configuring. And usually this means that a practitioner doesn't really have to do a lot to get values of it. But unfortunately, we couldn't really find the values here as like a reference value, so you don't really know how good the method and like the pre-training in the end actually performs. And yeah, we took this and found like these issues: small pre-training dataset sizes, non-state-of-the-art architectures, an okay-ish evaluation that could be improved with some more like robust datasets or NN Unit maybe as a reference. And then we looked at other papers, and we found like a very similar pattern, like also some maybe not state-of-the-art architectures, not that large dataset sizes of 5,000 subjects, and looked at additional papers where they, for example, use a lot of scans, like 110,000, which is quite large already. And then unfortunately, they propose like a new architecture in combination with their pre-training. So like the performance of the pre-training method is not really isolated. You can't really like judge how good it performs because usually ablations are lacking. And then also you can see down here, they evaluate on 3 datasets, head and neck tumors, and with 48 cases, and then like synapse of 30 cases, so BTCV again. So overall, like very, very small datasets and questionable results, therefore. So you don't really know like how good this method really is. Yeah, and doing this for a lot of papers, we found that this is quite consistent across the entire field of 3D medical self-supervised learning. A lot of them train with really small pre-training data sets. They use very different architectures, also oftentimes like transformer architectures, which at this point of time were really like a lot worse than they have become recently. And all of them also did different downstream data sets. They use different they use very little downstream data sets, and sometimes they also pre-train on downstream data sets. So even if they use the same downstream data sets to evaluate their model, you would not really be able to like make a distinction if one is better than the other, because one might have trained on it and the other might not have trained on it. And lastly, like as a chip in all the evals, from our perspective, they hardly did comparisons to NN Unit, so you would never really know if their training setting is really well tuned and well built. And with that, we compiled this whole list and found that basically a lot of different pre-training methods usually don't tick all the boxes. So either they have very small data sets, they have like a non-state-of-the-art architecture, so at this point in time, as I mentioned, transformers, or they evaluate it really poorly. So you would not really know, like, do pre-training methods work? Which one is the best? What is the current state? Was it a really difficult question? And down here, this is like us, where we try to like address these issues and like use large data sets and so on. Now, yeah, as I already foreshadowed, we answered the question that there's not really a convincing method. There's the methods usually train on small data sets. They don't train state-of-the-art architectures, and they don't really follow great evaluation practices. So we were wondering at this point in time, does it even work? So is self-supervised learning even worth it in 3D medical imaging? And with that, we set out to our first project, which was the revisiting MAE pre-training, which preceded the one that I will talk later about. And in there, we try to answer this question. We try to answer, does pre-training even work? for segmentation as downstream task. And we, at the beginning, set out to like limit our search space a bit. So we wanted to, of course, pick like a state-of-the-art architecture, and this is still CNNs. So we picked like a CNN architecture. We decided on training paradigms, and in the natural imaging domain, we found MAE pre-trainings to work really well, while a colleague tried contrastive pre-training and did not really see any improvements back then. And also like more fancy methods like DynoV2 are pretty optimized, and then transferring like these 2D methods to 3D imaging is really difficult because you run into a lot of engineering hurdles with your like VRAM constraints, so you can't do large batch sizes, and without like having to see like entire images, not being able to see entire images, and then also like the dataset size in general. So you can't just like take a 2D method and transfer it to a 3D imaging. So yeah, we picked MAEs, and then as evaluation, we chose to like be very rigorous, and we followed like the NN unit process. We picked a lot of development data sets at the beginning, which were not touched which were not like contaminating our test evaluation in the end, and yeah, had like multiple independent test data sets which were not used during the development phase. So basically, we optimize our like pre-training setup on these development data sets, and then see if this pre-training optimized setup transfers to the independent test data sets. Now, this whole project, as I like said in the beginning, was with a collaborator, which was a German startup called Floy, which provided us with their proprietary data, which was about 44,000 3D images of head and neck MRIs with like a lot of diverse spacings and acquisitions. And in order to make this data somewhat usable and not like shred our model with like sampling bad images, we did some like basic data filtering of removing very weird images that you would not really see during application. And with that like data set filtered, we went to the development cycle, which uses these development data sets to select some parameters, do training and fine tuning, and then like look at the results and iterate and choose like a really good setting. And through this development cycle, we basically ablated a lot of MAE parameters, which don't really matter too much for this talk, and a lot of fine-tuning settings, which we'll come later to as well. And however, through this like development cycle and through this process, we in the end got a model that showed really like reliable performance, and actually also performed better than NNUNet, which is these two columns here. And with that, we basically answered our question, which we wondered: does pre-training work? Yes, it does. And we can actually improve over like from scratch training using, for example, a state-of-the-art MAE pre-training. Now, this was a bit with some asterisks. So we had the finding that pre-training works, but we only know that it works for segmentation. And then we also found that masked image modeling is better than contrastive learning, given the baselines we selected. However, the baselines were rather limited. And we also found that the adaptation schedule was very important. And the big but of this was that the pre-training data set was still proprietary. So even if we published this work and other people would read it and find it cool and want to follow, they could not reproduce our results and our training setup. We also, during this paper, found that the inclusion into NNUnit to provide segmentation results was very like laborious, took a lot of hours and like manual work, which was really annoying and would make like the adaptation of like SSL really bad. And so this was like an issue. And also in this earlier work, we only evaluated CNNs and no transformers at all. So we did not really know. Maybe transformers perform well if you have large data sets and you do good pre-training with it. And this study did not answer that. And lastly, of course, we only evaluated segmentation. So this was also a big limitation. And with like this picture of the state of SSL, we decided to tackle a different question. How can we unify like the self-supervised learning domain for 3D medical imaging? And how can we enable follow-up research to be reproducible and to also have impact on the broader field? yeah, and this sparked our OpenMind work that I was invited here to talk about. So in this paper, we try to unify and enable SSL research in 3D medical imaging. And as like mentioned, there were like a lot of pitfalls that are still blocking SSL to become really prevalent in the domain. And in this work, we try to make SSL easier for developers. So we try to like get some large pre-training data set public that isn't proprietary. So enable like getting data easily for like a developer. Then we found the SSL development to still be difficult, because if you have large data sets, preprocessing and data handling is not that easy. Everyone publishes like their own implementation on GitHub, but it's very specific to their own data set. And if you transfer like their pre-training to yours, it might not work. So we wanted to like unify the implementations a bit. And lastly, we also found that, like, as I said, like the NN unit adaptation. So if you have your model pre-trained, moving it to a downstream application is really difficult and annoying. We wanted to tackle that issue. And from the user side of things, if you're just applying and doing some segmentation or imaging work, we wanted to make using self-supervised learning more attractive for users as well. And we identified a roadblock of the uncertainty in the space. So no one really knows what kind of method is the best, because everyone has their own data, everyone has their own downstream evaluation, evaluates on their own like architecture. No one really knows what was best at that time. And depending on what kind of like downstream problem you have, you might be more interested in segmentation and classification. And usually these papers would not evaluate both and like cherry pick like one or the other maybe. And lastly, also, like, even if there's like a pre-trained checkpoint, it might be difficult to integrate this into your workflow. And we try to like, at least we identified this roadblock as well. And yeah, we try to tackle these in this project. And starting off with these like large data sets being not available, we looked in the domain, looked like what kind of data is out there, and found like these 4 big what do you call it, like a big unified data set that you could just download it if you had access. However, ABCD is an NIH study of the adolescent brain cognitive development. So it's 41,000 brain MRI images. However, unfortunately, they are very restricted. So you need to like sign up on their portal and submit a project proposal, and then like some Gremium will look over it and check if it's actually like a feasible project, and then you might get approved. So since this is like conditional on having a cool research proposal, this might like limit reproducibility. Just imagining that if you propose a project and get rejected, you can't really use this data set. Then we have the NLST dataset, which is the National Lung Screening Trial, where there are 72,000 chest CTs, or low-dose chest CTs, but those are DICOM, and usually DICOM is very laborious to handle and very difficult to convert. Making sure like all the data is consistent and reproducible, and everyone like is able to convert it is not that easy. So we also went on from that. And UK Biobank, which is probably like the largest semi-publicly available data set, has more than 100,000 full body, brain, cardiac images, all MRI. However, unfortunately, like they recently gated their data to be only used in their research analysis platform, which is basically an online computing instance where you can buy credits, but you can't really download the data and integrate it into your workflow easily. So everything has to happen on their side. Also, of course, making like reproducibility an issue. And honorable mention here is CT-rate, which came out recently, but this was too late for our project, unfortunately, back in the day. So what we found is that all the different data sets are not really like publicly available easily or usable easily. And then we stumbled across OpenNeuro, which is a neuroscience platform where most of the time fMRIs are imaged. So some functional studies of the human brain. But since every functional image is usually registered to some T1 image, all of these fMRIs also come with like at least one structural image where the fMRI is usually registered to. So we were lucky and found a very large database, which also was CC0 licensed, so you could do whatever you like with it. And lastly, since this was like composed of more than 800 different public datasets, we were able to get like a large diversity of pre-training data, for our project in this case. And what we did is that we, of course, crawled like this platform and pre-processed whatever data was there. We also took the diffusion images that they had, which are 3D plus time, and pre-processed them through a normal diffusion imaging processing pipeline, where we, in the end, got T2, mean diffusion, and fractional and isotropy maps, which are static 3D images that can be derived from this 3D plus time diffusion image. Overall, this, of course, ended up in 114K 3D brain MRIs, for which we also did like some post-processing, trying to identify images where there's, for example, anonymization in the image. So in case you want to train an like an MAE objective, you can ignore these regions where there might be like some structure cutaway or some like face blurred. And here's like a small stat of this data set. You can see that 50% of the entire data is contributed by 12 data sets, whereas 81 make up 75% and 283 make up 90% of the data, with the long tail just contributing the last 10%. And this in the end became the OpenMind dataset, which you can find on Hugging Face and directly download for whatever project you like and use as you will. Now, given this pre-training dataset, we tick the first box. We have a dataset that everyone can use. Great. Now, what are the remaining like roadblocks of it? And first of all, we decided to use this dataset then to develop a large benchmark and test different methods. So how to read this plot here is that all these 4 first rows are trained from scratch. Above is the NN unit baseline, and down here is the same architecture trained for either a longer period or for a shorter training schedule. And then we have, highlighted in blue is like the longer schedule here. Then we have the data sets. So we have different data sets, since we are all brain, that are in the brain region as well. We have some stroke lesions, brain metastases, head and neck tumors, whatever's available. And then we also have some more out of domain regions and data sets. So for example, we have a heart MRI. We have some abdomen CTs with AMOS and KITS, for example. And these in distribution and out of distribution data sets are averaged down here, yielding like these columns over there. Yes, and the first finding that we had, of course, is that masked autoencoding is quite strong. So compared to from scratch pre-training, from scratch training, the pre-training with masked autoencoders down here performs really well. In particular, on average in domain, all of these methods are performing very, very strongly. And if we go and compare this to like contrastive methods, for example, VOCO, Swin Unit R pre-training, and SimCLR, we can see that those perform not that great, with some pre-training methods even being worse than training from scratch. And it's maybe also to note that the Swin Unit R here is not to be confused with the architecture itself. So there's like one architecture and one pre-training paper. And in the pre-training paper, they propose a certain method, and this Swin Unit R here refers to the this pre-training method and not the architecture itself. Because like, as you can see up here, like all of these methods are using the same architecture. Comparing to previously, we also moved to transformers. So we trained a Primus M transformer, which was also published rather recently at the point of this paper. And as you can see, these contrastive methods perform really, really horribly in this case. We are like substantially worse than training from scratch. And again, the MAEs perform really well when using a transformer, and those ones perform quite a bit stronger than the from scratch trainings. Now, overall, we found the MAE, like the basic MAE objective to be, or pre-training method to be the best, quite consistently. And yeah. Now, having evaluated segmentation, we also wanted to be a bit more holistic this time and try to look at classification, which is not really a well-established domain. So unfortunately, so we have Brezeng L and Primus again. So this time they're not above each other, but like left and right. And then we have these data sets here, which are an MRNet. It's like a knee tear data set. Then RSNA, which is a classification of spine fractures. And then ABIDE, which is an autism detection for either autistic brains or not autistic brains. And again, two different metrics that we evaluate here, average precision and balanced accuracy. And as I was about to say earlier, we have the issue in the classification domain that there's no real NN unit in there. So we don't really have like a from scratch auto-configuring pipeline that allows us to really train something and see how good one would actually get. This is probably because classification is a very, very difficult problem in 3D, because you have very little data. You have hardly any supervision signal, because like one image is like paired with one label, whereas for segmentation you usually have like these masks and like many different pixels, which give you some supervision signal, allowing you to train properly. And in classification, you don't really have that. So you need usually a lot of data. And hence, also targets diverge a lot. So autism, I don't know how one would detect it. I don't know, like a small, it might be a global thing that you can see. Honestly, I don't know. But of course, this spine fracture thing will be very localized, very small. So like the automatic configuration might have to be very different for these different data sets. So long story short, there's no real like baseline we could have easily implemented here. And therefore, it's hard to know overall of this table if our configuration is great or not. And we just try to do our best and be consistent in our setup. Now, this being said, we can look again at from scratch training, and we can see that CNNs perform a lot better. So over here, we get like means of 63, 64, whereas over here, we get like 57 and 61. So overall, CNNs perform a lot better than transformers in classification, at least, which is somewhat surprising given that usually you assume transformers have global reasoning. Classification might be more of a global task. Transformers should be better. But empirically, we just found CNNs to still be really, really great in this. Now, even further, we find that contrastive pre-training is, for the case of classification, a lot better, which is also not really surprising. It's a finding that is mirrored in the 2D natural imaging domain. You usually see that contrastive training performs really well there. However, dense reasoning is not really like a strong suit of contrastive methods, because you just like learn global pairings, or like you just learn like a global objective. So there's no real dense reasoning happening. And this is also mirrored in our results. So we see also CNNs and transformers to benefit of it, with CNNs benefiting a lot more than transformers. And finally, we also see the same story as usually, that MAE pre-training is not really that good for classification. Instead, we just have like sometimes lower than from scratch results here, or at least rather consistently. And for actually for both CNNs and transformers, we see that MAEs don't really allow that good of or don't learn that good of like global embeddings. So this means that comparing the classification and segmentation results from the two tables, that there's no real pre-training that is good at both. And yeah, there's like a lot of research gaps still in this space here. Now, let's skip that. Or maybe, yeah, okay, maybe let's talk about it. Because regarding the adaptation, there's a lot of different degrees of freedom as well. We didn't really like highlight this in the previous or in the pitfalls at the beginning, but if you ever like train your model and pre-trained your model, there's a lot of different ways that you can adapt it. So for example, for classification, you can decide to do like some mean pooling to get global embeddings from some like dense encodings, or you can maybe have a transformer that has a classification token. You don't really have like one way of getting a global embedding. And the same also applies for how you do segmentation. In our case, we try to unify this as well. We try to like define two exact ways how we pre-train our CNN and how we do adaptation with our CNN, and how we pre-train our transformer, and how we adapt our transformer in the end. And what we did in the case of CNNs is that we have usually like an encoder-decoder unit style architecture, and of course we use that. However, the CNN decoders were never transferred. We just like after pre-training threw them away, because some of the methods like contrastive training does not train a decoder at all. So if you do a SimCLR, you just have your CNN encoder, and then you do some like pooling and get like a global embedding, but you never really train like a decoder that reconstructs like a dense space. So you could not transfer that. And in order to be consistent across pre-training methods, we try to eliminate this factor of variation and said, okay, we only keep the encoder and then always do the same. We initialize like a decoder from scratch, either for a CNN or a transformer, but it has to be consistent. And further, we also have the question of, okay, I have my pre-trained encoder, CNN or transformer, and I have my decoder. How do I train it now? The CNN decoders or transformer decoders are initialized from scratch. So if you just start training, you're going to get like a lot of bad predictions at the beginning, and your loss and your gradient will be very large. And if you maybe choose a bad learning rate schedule, you might just unlearn whatever you learned during pre-training. So this aspect of pre-training is, of course, not really unified across papers. So we try to set a few standards for how do we do the fine-tuning and adaptation of our pre-trained models. Now, what you can see here is in dark blue, the learning rate curve of encoder and decoder. In light blue, it's like the learning rate when we are just training the decoder. So for this case, like the encoder remains frozen. Here we have some joint warm-up, and then I think it's light blue actually, so like some decoder warm-up and then joint training with a normal schedule. And here we have a decoder warm-up and then a joint warm-up and normal training. And otherwise we have like this learning rate valley here. Now, since we wanted to be fair, we tried to evaluate these different learning rate schedules. In segmentation itself, we already found that CNN can usually easily handle like a default training schedule where you just start with a really high learning rate. Whereas if you do transformer training from scratch, you usually want to have like some warm-up and then train your model. Otherwise, you just run into training instability. So you just want to, you know that we knew that for transformers you needed this. So we tried to ablate this for both the architectures and all the methods, which is provided in this table here, where we check the different data sets and different fine-tuning schedules, which you can see here in these rows. And then up here you can see the different methods. And we try to average the overall performance of all methods to be somewhat fair to all methods. And then we chose like the best average value in overall dice performance. And this became the default startup. This became the default learning rate that we adapted our pre-trained encoders with. So what you can deduce from this table is that having a frozen encoder is really, really bad. So whatever kind of embeddings you currently create and get from your self-supervised learning methods is not really usable out of the box. You have your frozen encodings here that are like substantially worse. Then for the CNN setup, we saw that like the sawtooth pattern here, where you go warming up the decoder and then warming up both is the best. And then for the transformer, we found that a different kind of warm-up schedule is better, where you just warm up everything together and then train the transformer. And overall, if you look at the performance variation back here, you can also see that the schedules are very important. So compared to the overall from scratch, compared to like how much performance gains you get, which is usually like 1 or 2 dice points, having a variation of like 1 point in performance in the end can mean that either your pre-training works or it doesn't. So we found this to be very important, and hence it's also a signal and a problem of the domain that if you don't have this unified as a factor, it might just be that some new method that you build and that is published just uses a different fine-tuning schedule, and it is not really better than your baselines because the baselines just don't work with this schedule, or that this architecture does not really like this schedule. So this is like an important underappreciated aspect of the entire pre-training domain, I think. Now, summarizing the findings of the paper, we find that local tasks are really good with masked image modeling. So if you do a pre-training with masked autoencoders, you're great. If you want to do classification, use or some other global task, do contrastive pre-training at the moment. But unfortunately, there's no real good pre-training that can do both. So we're not really at DynoV3 territory yet. We just need to like push our methods a bit more to get something that is really generalizable. Further, we still see, even with like training on 100,000 brain MRIs, CNNs are still superior to transformers. So at least we found that the data set scale that we train our transformers with is not really the issue. There might be some other underlying problem that is holding the transformer back in medical imaging. But I'm quite confident to say that data is not the issue for transformers in medical. Further, in the paper, we also found that if you fine-tune for longer schedules than shorter schedules, you also lose performance. So it's not always worth it to train 250,000 steps. Sometimes it's better to just train 40 or 50, and then you might be better overall than training for the longer period, in particular with pre-training. And also, as the last point mentioned, fine-tuning schedules are really important and a key component of pre-training in general. Now, this paper basically ticks 2 boxes for making SSL more attractive, because we were hoping to shine a light which kind of pre-training method to use, CNNs or transformers as architecture, what to use for segmentation and classification. So we are providing a lot of insights. And if you're a user and you know your problem is like segmentation or classification, you hopefully now can like look in the field and see, hey, these checkpoints exist. This one is a contrastive pre-trained method. I'll just take it and use it for my task. But unfortunately, a few issues still remain, which is like the pre-training framework, and then that integrating like methods and checkpoints into NNUnit is really annoying. And this is why we also used and published our framework, which is called NNSSL. It's currently on our DKFZ GitHub, and contains all the pre-training methods and the entire development framework that we use to like train all these encoders. And it also comes with like the features that it can handle the pre-processing of data. So if you download the OpenMind dataset from Hugging Face, you can use that quite easily to pre-process your data and get a working development environment off the ground really, really quickly. Further, this also also includes the pre-training, but it also more importantly allows to easily adopt your pre-training checkpoints into NN unit. So if you want to do segmentation, I think it's really worth it to check out our repository, because you can just pre-train something, and then if you have the pre-trained checkpoint, easily migrate it into NN unit and use it directly there. Actually, you can already enter a GitHub link in our NN unit draft, our NN unit branch, and then it will automatically download a pre-trained checkpoint from Hugging Face and pre-process the downstream data set similarly and train your model with the pre-trained checkpoint. So this is quite a nice resource, at least in my opinion. And yeah, this is the downstream framework where you can, if you enter the URL of some GitHub checkpoint, Hugging Face checkpoint, you basically download it automatically and then train your NN unit with the pre-trained checkpoint. So should be as easy as entering 3 lines. You just say NN unit v2 plan and preprocess as you would do previously. Then you call preprocess like NNSSL with some like dataset identifier, name how you want to call your pre-training, and the path, which can be the Hugging Face URL. And then you just call NN unit v2 train pre-trained, and then everything will be taken care of, and you will get your pre-trained NN unit segmentation model out. And yeah, also, if you're a developer and if you're interested in contributing to the self-supervised learning space, you can easily upload your own checkpoint onto Hugging Face. It even supports that you put a citation in the checkpoint itself in like a dictionary position, so just a key value pair. And then when someone else will use your checkpoint, it will also print out a message like what kind of pre-training was used, so you can get attribution. And if you build something that every NN unit user will use, you can get a lot of exposure, of course, and hopefully get your pre-training into a lot of hands. And yeah, through all these resources, we ticked all the boxes that we were setting out to tick at the beginning of the project. And yeah, we also used these resources already a bit to test and to do a Mikai challenge recently, which concluded in October, I think. And in case you're interested, it's the SSL3D meets OpenMind challenge. And yeah, we found similarly, as a small teaser, that at least in the current domain, we have a lot of methods that are good in segmentation, but are not that great in classification, which is over here. So you see segmentation rank, classification rank, and you can see that methods that are good in one usually go down, and methods that are bad in segmentation are oftentimes good in classification. And yeah, so the field, at least method-wise, is at the same point as we are, and there's no real method that's great at everything. And for transformers, though, we see a few methods that are not that bad, but overall performance of transformers is still really not that high. And I think there were not that many participants in the transformer track as in the CNN track. And with that, I'm also happy to take any questions, and I'm done. Yeah, let's just stay here.
Thank you so much, Tassilo. That was really nice presentation, pretty in-depth. Anybody has any questions, please feel free to type in, feel free to ask Tassilo. Yeah.
Let me just open this.
I have a question. So
yeah, sure.
I see that you've used contrastive methods and masked image modeling methods, right? Like masked autoencoders. So I was wondering, have you had the chance to try out the Dino methods?
Do you mean Dino v something, v2, or the V2? Normal Dino? Dino v2, we did not really have the possibility. I think back then, I don't think there was an open source repository for 3D v2, Dino v2. And just if I mean, we looked at it a lot and we were like thinking about it as well. However, DynoV2 is like heavily engineered usually. So you have like a lot of different moving parts that don't translate super well to potentially small batch sizes. And then transferring all of these things over into 3D, I think is really hard. And I think it's really difficult to make it work really well. I would be surprised if it works super great for dense downstream tasks at the moment. And I have not seen any like super convincing results from a paper that does claim they do DynoV2.
Yeah. Thanks.
Great though. I think it would be great to have more like general purpose pre-training methods actually.
Yeah, I agree. That's true.
Yeah, thank you, Ratna. Tassilo, maybe one question would be like, did you like try out MedSam?
MedSam as a pre-training, or no, we did not. MedSam. I mean, we had a benchmark on it for interactive segmentation, but it's a bit problematic because MedSam 1 was is a 2D method.
Yeah.
So we tried to keep it to 3D encoders, and if we introduced like a 2D method, I think it would have been very confusing and also very unfair to compare, because usually in our results we always see that methods which are native 2D perform like at least 3-4 points worse than anything in 3D. So it will be really hard for this method to outperform whatever is in 3D.
Yeah, I think that there's a 3D version of MedSam as well. Like, give it
yeah,
a try.
I think so. I think there are quite a bit of recent interactive methods.
Yeah.
But we have not really looked into how we can like use those directly for segmentation or like some adaptation in this case. I feel like a lot of methods exist and it's really hard to adapt them to anything, which is, I think, the biggest downside of this domain, because we don't really have like not everything is like 2D images and RGB, so it's really hard to just take an encoder and drop it in somewhere.
Yeah. Anybody has any other questions?
I have a question. So you mentioned that the benchmark shows like for reconstruction methods, it excels for dense tasks and contrastive for global tasks. So I was thinking, do you believe that a multitask loss with some explicit planning component, like there's a method called CAPI, which is kind of a natural evolution of MAE. So do you think having following CAPI's approach could be a key to achieve better generalization across segmentation and classification tasks on this data set?
So to repeat, because I'm not quite sure I caught everything, you were asking if like combining different objectives during pre-training can maybe get something that works on both. Is that about the?
Yeah, so basically there's another SSL approach kind of similar to MAE, which is called CAPI, with basically adding CAPI, yes. Yeah. So I was wondering if
yes, I think it's great.
CAPI uses like a planned augmentation strategy, and also it combines multiple pre-text tasks. So I was wondering if that could help in generalizing between classification and segmentation.
Yeah, I think CAPI is cool. And I've seen it come out like I think in February or March this year, right? So it's quite new and a simple version of DynoV2, according to the authors. So I think it's a worthwhile option to investigate. I think it's also designed in a way that it's very similar to iBot with some compute efficiency gains and like some additional like clustering. So I think it's really cool. I think it might be really good in 3D if you find a well-tuned configuration of it. I'm not really sure how well like everything translates. We've tried like to hack like a simple version of that together back when I was doing my internship. But of course, like I was working on something else and didn't really have the time. But I think if you spend some time and work on Copy, I think it's has great potential. I think it's a lot easier to get going than Dino v2. And iterating from there would be like the next step, of course. But I think it would yield embeddings which are much better for global reasoning and local reasoning. So I think it would be like maybe one of the first where you have both like boxes ticked.
Yeah, I think it's more robust in terms of capturing the functional networks. That's what they claim. So I think that might be, I don't know, it might be more robust, and it will be interesting to see how that will work.
Yeah, it would be great to see a bit more interest in the entire domain. I think currently it's a bit slow. Not a lot of people are working in it, and I think there's a lot of progress to still be had. In particular, the classification side of things is really difficult to train in medical, and there's not really a lot of established frameworks. So if you have a good pre-training method and a good like base embedding that you can iterate from, I think you can make all these small classification data sets and problems a lot better. And I hope that this gets a bit more attention, because it would be great to have like a cooler classification stack. Where segmentation, it feels really hard to edge out performance. Sometimes you're in a noise regime where you're probably like just trying to overfit better to what kind of like pattern the radiologist follows than actually being more sensitive to like structures. So I think classification might be like a cool domain where one can also do like SSL research into, and then hopefully get better methods out of it.
Yep. Do you have any other questions? All right. I think let's wrap it up. Thank you so much, Tassilo, for taking out time and giving this amazing talk. If anybody has any questions, feel free to follow up on our Discord, and we will be sure to forward those questions to Tassilo, and we can get back to you. Thank you so much. Let's see you all next week with another guest speaker session.
Thank you so much.
Thank you. All right. Bye.